Hi, this is Cam Calderon. During my previous video, we covered the theory about smoothing forecasting, and in this short video clip, we are going to cover the topic of a more practical case of Amtrak ridership. Amtrak is a train line, so we are going to analyze how we can forecast using smoothing with the Amtrak dataset. So let's go to my full desktop. So we have this example, yes. Here we are starting our algorithm with alpha equal to 0.2. As I said during the previous theoretical session, usually we start with an alpha equal to 0.1 or 0.2. The closer alpha to 0, that means that smoothing is going to be like similar to moving average, right? We are going to give, if alpha is closer to 0, we are giving to all previous observations like the same weight, the same importance. So here we are using this the equation that we said during the previous video for the forecast in time t plus 1 equals the forecast in times t plus alpha times the error term in times t. Yes, so this is exactly what we are doing here, right? So this forecast, let's say that this is time 1, time 2. This forecast in time 2 is going to be equal to the forecast in time t, which is 1709, plus an alpha that we need to calculate, or that is given here, times this error term. Okay, so for the next forecast, then we are going to decrease a little bit the forecast, and these are the actual values. We use the actual values in order to get to know the errors. So here we have in this slide the indexes or the indicators of accuracy. So MAPE or MAPE is moving average percentual errors. We have as well the MSE, the moving the mean errors, yes, mean standard errors. And we have many other measures of accuracy. I think MAPE is one of the most used, and MSE as well, together with RMSE, which is root mean square errors. So we have here the mean square errors as well as a measure of accuracy. The same, the closer to 0, these figures, I think that is indicating us that we have like a beta forecasting model. Yes, so the model is fitting better the data. Okay, in this picture that we have here on the screen, we have the actual values in black and our forecasts. Again, the difference between the actual values and the forecast are called errors. And these errors are as well named residuals or the remainder. They have like 3 names, but you can use any name. After making this subtraction, we are able here to plot what are the errors in each time series for these months. Yes, so that is what we have here, like an estimation using a smoothing. Yes, and here are the remainder. Yes, one of the issues that we covered before is that we want to remove a seasonality. Before going, because well, as you remember, this algorithm has an assumption that we only have a trend and noise. Yes, obviously you can see here that we have actually a lot of seasons in this ridership. So in the next slides we are going to cover how to remove the seasonality in order to apply the method. Before that, let's go to see a short video about the Amtrak train line, which is going to give us a little bit of idea of what is going on in the actual recent times in terms of the ridership. So that was the video about the Amtrak ridership. As you can see, the actual ridership has dropped 97% after this pandemic. So all these train lines are actually like very bad financially, and well, I think the government has in the United States have had to bail out all these transport businesses, as so in the UK as well. So I say that before that, in order to run this algorithm, the algorithm that we have in here, in order to calculate smoothing, we need actually to take out the seasonality. Yes, we need to remove trend and seasonality from the data in order to get a better forecasts. So removing trend and or seasonality, I have this picture here just to say that well, winter is a season, so sometimes we want just to smooth, to take out the seasonality from the data. So the first approach that we have is differencing. Yes, so here in this picture we have, for instance, a person like a boy taking measures of itself and is actually subtracting his growth, his actual growth from a previous one, right? And we do exactly the same with our data. We do yt minus 1, meaning that the observation today is subtracted from the observation in the previous observation, say yesterday, right? So that is lag 1 difference, but actually you can use lag m difference. So for instance, if you have data in months, you can actually use the lag of 12 months. So being yt November and yt minus m November last year, right? So that is the another way to remove the seasonality when we have like monthly seasons. Also, we have double differencing. So we apply this when we have problems of too much seasonality in the data. Yes, so we applied 2 times differences over the series in the fashion that we covered here in this place. So we can make a lot of differences in order to try to carry on smoothing more the data. Here we have examples with a lag 1 differentiated series, yes, lag 12 differentiated series, and here lag 12 and lag 2 and lag minus 1 differentiated series, right? So as you can see, if you apply a lot of this technique, what you are going to end up is with data that is fluctuating around 0, and that is a good thing, because that is going to allow us to like make a better prediction with our data. The approach number 2, in order to remove the seasonality, yes, in this Amtrak setting, this Amtrak example, is just to well, like generate a regression model. So if you have a regression model, what you do is simply subtract the linear regression or the regression that you have used in order to detrend and deseasonalize the data, just a subtraction, and then you will end up with certain errors. Yes. So instead of using the previous subtraction between observations, here what we are doing is to fit a regression model to try to detrend the data, so you will end up with something, a line around here. Yes, and so then we can apply afterwards the smoothing methods. The approach number 3 is the ratio to moving average method, which uses moving average to remove the seasonality and also generates seasonal indexes as a byproduct. So we are not going to go into this ratio to moving average method, but I think what you want to know is that is in there in case you want to use it in the future. So in summary, deseasonalizing and detrending the data for forecasting is one of the most common techniques that we use in forecasting. And we, in forecasting a series with seasonality and or trend, we can use moving average or exponential smoothing. Yes. So first, then we do a detrending on or a deseasonalize of the data, and then we forecast. And I think that is the main message of today. Yes, the summary is that in order to use the algorithm that we covered during the theoretical part, we need to detrend and or deseasonalize the data. In my next video, we are going to cover a practical exercise in which we are going to use R RStudio in order to run a forecast using the Amtrak ridership dataset. So please, I will see you in my next video.